Well, hello. In this video, we're going to be solving exponential and logarithmic equations. This is section 4.4. All right, we're going to tackle solving exponential equations first. And contained on this first page are two different strategies in which we can solve exponential equations. The first method or strategy is getting like bases. We'll do a few examples of that method. And then down here, we look at solving exponential equations using logarithms. All right, looking at the first strategy right here, okay, these are two examples already worked out for us. This says, let's express each side of the equation as a power of the same base. This formula tells us that if we do have the same base, that the exponents have to be equal if we have equality. We've worked on this a little bit in previous sections, so hopefully this strategy right here will seem familiar. In example 1, we have an equation that already has like bases, so the answer is going to be x equals 3. In example 2, we have this exponential expression right here, and then we have it equal to 125. We want to get the same base, so we rewrite 125 as 5 cubed, like it's done over here. Once the bases are the same, we can remove them. We take the exponents, we create a little algebraic equation, and then what we're doing here is we're solving this equation for x. So I'll add some things here to this example. If I'm going to get x by itself, I'm going to add 6 to both sides. And the result is 3x equals 9. To continue solving, we divide both sides by 3. And the result is x equals 3, the answer. So let's try some of our own down here. In example 3, we have this exponential equation. 81 is bigger than 3, so let's first start to write, if we can, 81 as a power of 3. 81 can be rewritten as 3 to the 4th power. Use your calculator just to start multiplying 3's together until you get to 81. Our answer is 4. In example 4, I look for the larger base 8, and I think to myself, can I rewrite 8 as a power of this other base? Well, I know that 4 to the 1st is 4, and I know 4 squared is 16. So no, I can't rewrite 8 as a power of 4. So in this case, I don't think we've seen one like this. We want to think about another base that we might be able to use where both 8 and 4 can be made powers of that base. So for example, 8 can be rewritten as 2 cubed. So if 8 is 2 cubed, I'm going to kind of put that in parentheses, keeping the exponent x plus 2. 4 can also be rewritten as a power of 2. 2 squared is 4. So replacing 4 with 2 squared, keeping the exponent. We're going to apply some properties of exponents here. We want to get the parentheses removed from these problems, so let's take this power to a power. So we're going to multiply 3 into the x plus 2. So I'll have a base of 2, and then distributing 3 into x plus 2 results in 3x plus 6. Likewise over here, let's multiply these two powers together. So we'll keep the base of 2, distribute 2 into both of these terms, and we're going to get 2x minus 6. So now we have the same base, so let's equate the exponents and solve the algebraic equation. All right, in this situation right here, I'm going to subtract 2x from both sides of the equation. So collecting here, when looking down vertically, I'm going to get just 1x, then I still have the plus 6, and then over here I still have the negative 6. Next thing I'm going to do is I'm going to subtract a 6 from both sides of the equation. Have to kind of squeeze the answer over here. So x is going to be equal to negative 12, and that's our answer. Negative 6 minus 6 is negative 12. Okay, let's look at example 5. Oh, it's getting kind of crowded. Okay, when I look at 5 and I want to solve this exponential equation, we're trying to use the method of like bases. Well, when I kind of look at 125 here in the denominator, that's the larger number compared to 5, so I know that 125 is also 5 cubed. So let's just leave the left-hand side of the equation alone while we work on this side of the equation. This is 1 over 5 cubed. From our previous work, though, we see that we want to bring up 5 out of the denominator. Adjusting to a negative exponent. We're at the point we want to be where we have the same base, so we set the exponents equal to each other. You can subtract a 2 from both sides. Don't forget to bring down this subtraction now as a negative. Collecting here is -5. Divide both sides by -1. The result would be x equals +5 is your answer. All right, example 6. Can we rewrite 32 as a power of 4 to match this base? No, 4 squared is 16, but 4 to the 3rd power, the next integer exponent, would be 64. That's too big. So we're back to kind of like what we did on example 4. 4 can be rewritten as 2 squared. Don't forget to keep the exponent of x. And if you went to your calculator and just started multiplying 2's together, you would see that it takes 5 multiplications to get to 32. 2 to the 5th is 32. Okay, let's go ahead and tackle this work right here by multiplying these two exponents together. We have resulting same bases. Set the exponents equal, divide both sides by 2 to isolate x. So my answer is 5/2. Or 2.5, whatever form you want to leave that in. All right, one more example of using the method of like bases to solve exponential equations. Notice the base here is e, and there's also a base e here. The problem is that this e is in the denominator of a fraction. So let's bring that up to the numerator. When you bring up e to the 2x, adjust and make the exponent -2x. Same bases. Set the exponents equal to each other and solve. At this point, I think I'll add a 2x to both sides of the equation. That'll keep my x term positive. Remember, this is 0. When you collect here, we get 3x. And then don't forget the +4. Subtract a 4. And divide by 3. All right, that's solving exponential equations, trying to get the same base, equating the bases. All right, in method 2, we're going to see another strategy that we're going to want to use if we cannot get the same bases. And just also as kind of a side note, I can actually use method 2, what we're going to learn down here, to solve any of these problems up here. So once we learn about solving exponential equations using logarithms, if you don't want to use this strategy, unless you're otherwise directed to do so, to use this specific strategy, you can solve all exponential equations using this one-stop shop right here, this one method. All right, method 2 says not all exponential equations can be rewritten with like bases. All exponential equations can be solved using this method. Here are your 5 steps in solving exponential equations using this strategy. First thing is we want to isolate the exponential expression. So if this were our problem right here, this is the exponential expression. You'd have to subtract a 2 from both sides of the equation. Step 2 then says to take the common log on both sides of the equation for base 10. Take the common log for base 10. Well, this is not base 10, this is base 5. Then it goes on further state, take the natural log, the ln, on both sides for any other base. So for this equation right here, we're going to take the ln, or natural log, on both sides of the equation. So the next step was, working off of this equation, put ln in front of both of the terms in this equation. Then it says simplify using properties of logarithms. We had 3 logarithmic properties. We went Product to sum, we went quotient to difference, and we went power to factor. And those were in notes 4.3. So if we're here at this step, what's happening from this line to this line? Well, nothing changed over here, but I see what happened is we're using a log property that allows us to take that power and make it a factor. We want to get x out of that exponent position because that's what we're solving for. And then it says solve for the variable. Well, at this point, if I just divided both sides by ln of 5, which is a number, ln of 5 over here, that same number, I would isolate x and I get this fraction. This is your exact answer. If you go to the calculator and get a decimal approximation, it's just that, an approximation. It's not exact. So we're going to do all the algebraic work. We're going to set up maybe a complicated problem here, but then we're going to go to the calculator last to get the decimal approximation to 3 places. All right, example 1. Well, first of all, let's just look at all of these together. These are 6 examples right here of exponential equations that need to be solved. I need to find x in all of these problems right here. So I realized that I can't use strategy 1 because 8,000 cannot be rewritten as a power of 10. There's no way on my calculator I can hit 10 times 10 times 10 times 10 and get a target answer of 8,000. I can't use strategy 1 and get the same base. So what's my strategy? Isolate the exponential expression, which it's already isolated. Unlike in problem 3, where we need to divide the 9 out to both sides before we can work with the other steps of this strategy. So in number 1, step 1 is already taken care of. The exponential expression is isolated. Okay, step 2, take the common log on both sides for base 10. This is base 10, so what it wants me to do is put the log, or base 10 log, in front of 10 to the x equals, and then put log in front of 8,000. Okay, step 3 says simplify using the properties of logarithms, which just means let's take this exponent that we're solving for, and because we have a log property that says power to factor, move the x in front as x times log of 10, and just bring down the right-hand side of the equation. Okay, this is just a number that we could get on the calculator, so let's divide out that number from both sides of the equation to isolate x. Okay, unfortunately, we cannot divide 8,000 by 10. We go straight to the calculator. So from this exact answer that we have, we go to the calculator. Just don't forget to put parentheses, okay, around the numerator, but more importantly, around the denominator. If you forget parentheses around the numerator, it's not going to matter. You're still going to get the same answer. You can try it. Try calculating this decimal approximation without parentheses on the numerator, but for sure on the denominator. And reminding you too that most calculators, when you hit log, will do an open parenthesis. So make sure you're closing the number, but then you're also closing the parenthesis you have on top for this open one here. Okay, so just practice with your calculator. The resulting answer should be 3.903. Example 2, we want to solve this exponential equation. I cannot rewrite this as a power of e, so we're going to have to use this method too. I see base e, it's not base 10, so I'm going to put ln ex ln 0.83. Using a property, x times ln of e. Again, if you found this value, it's just a number. Let's divide ln of e from both sides of the equations. Going to your calculator, making certain that you at least have parentheses in the denominator. The resulting decimal approximation is this. Example 3. Step 1 of this strategy is to isolate the exponential expression. Well, this 9 does not get multiplied into the 2. We have to follow order of operations and do the exponent and then the multiplication. Okay, so don't think that you can ever multiply these two together and give the 18 a power of x. It doesn't mathematically work that way. Let's first of all isolate the exponential expression, dividing both sides by 9. Okay, at this point, I'm going to go to my calculator, and if that's a nice number, I'll record that nice number here. But if it's not a nice number, if it's a decimal that doesn't repeat or end, or is just kind of some kind of weird decimal that has a lot of decimal places, I'm going to just bring down that fraction. I'm going to save all my calculator work to the end. All right, it doesn't equal a nice number, so I'm just going to bring that down, okay? All right, so what log should we put on both sides of the equation? Quite honestly, it doesn't matter. You could use the same log, log or ln. I would use either one of those two because you have a calculator keystroke, a calculator button for log and ln. We don't have log base 3 on our calculator. We don't have log base 4, so we commonly use log, or ln because those are the two buttons that are on our calculator. You could do log on both sides. You could do ln on both sides. It won't matter. So, but following the steps that they show us, I'll just go ahead and bring in the natural log on both sides of the equation. Now be careful over here and rewrite it as a fraction. And I'll just rewrite this. Okay, we want to solve for x. We're multiplying by ln of 2, which is just a number, so ln of 2 here. And I don't know why sometimes I use cursive and sometimes print. It doesn't matter. Ln of 2. Divide out. This is pretty cumbersome, so be careful on your calculator. You could find this value first if you wanted, and then divide by ln of 2. But this is your target decimal approximation. Okay, so if I'm doing this on the calculator, I'd probably do another open parenthesis and closed parenthesis here, and an open and a closed here as well. All right, number 4. This exponential expression is already isolated. I'm not adding anything to it in front or multiplying it like in example 3. So I'm ready just to jump in and take the natural log on both sides of the equation. Notice that this exponent is more than just x, but it also can be moved to the front. However, when you move this exponent to the front, it would be wrong to write it this way, because this almost looks like you're just multiplying ln times the 1. So if your exponent is more than one term, like it is here, it's 2 terms, let's make sure and put that in parentheses. Okay. So we're just bumping up the rigor a little bit. Okay, so what do we do next? Well, I'm going to go ahead and divide both sides by ln of 3. So I have 2 factors here. Let's just go ahead and divide out ln of 3. Another strategy, you could have distributed that in, but it might have made a little more work for us. Let's go ahead and divide those out. Now I don't need the parentheses here. I'm just going to bring down x minus 1, and I have this fraction right here. To get x by itself, let's add a 1 to both sides. Go right to your calculator, find the value of this fraction, and then add 1 to it. The result is 2.771 to 3 decimal places. Example 5 is going to be similar to example 4. At this point, example 6, it's pretty complicated. It's involved, okay, the worked out solution is on my key for those of you guys that want to look at it. Just making a judgment call here. I'm going to say I won't put any of these types of problems on homeworks or tests. So if you want to look at it on your own because you're intrigued, that's fine. But it's pretty involved algebraically. Okay, but just based on our situation, I think it'd be best just to kind of limit some of these problems right here. Let's focus on this right here based on where we're at in our, like I said, our current situation. Okay. All right, so we just looked at 2 strategies for solving exponential equations. Okay, so we're done with that. Now it's time to turn our attention to how do we solve log equations. When we have an equation with log in it, what are our strategies? Do we have multiple approaches? Yes, we do. If you look at this next sheet right here, we have one method right here that asks us to get like bases on our logs. So looking at all 6 of these problems, we're going to use this same strategy to solve these log equations. If you turn the page to the 3rd page of this, you see that method 2 is kind of fallen on the 3rd page. Method 2 to solve a logarithmic equation, and the steps for that are given right here. So we'll look at both these methods. So we'll go back and figure out how we can solve a log equation using the method of getting like bases. So it says if we have the same bases, let's set the arguments equal to each other. Goes on to say, if there is more than one logarithm term on either side, you must condense, based on 4.3 notes, put together the expression into one log on that side. Make certain the coefficient is 1 for each log expression. Be sure to check proposed solutions. A quick reminder that when we were introduced to log functions, we were told that the argument, which in this case up here would be called m or n, these are both arguments, that these values had to be positive, greater than 0. So when it says to check our proposed solutions, at the very end, when we get an answer, we're going to take our answer, replace it back into the original problem, and see and make certain that we don't get any negative arguments, because if we do, then that is not a solution. All right, so just kind of look at all 6 of them. It's good to look at all 6 of them together if you would kind of scan your page. Okay, for this problem right here, we're ready to jump in and solve this problem, meaning the coefficients on this log term and this log term are both 1. So that was one of the things it asked us to make sure and do. Okay, look at number 2. This coefficient is not 1, it's 3. So we're going to use a property to move that from a factor back up to a power. When you scan the rest of the problems down here, I'm looking right in front of log or ln. I want to make sure that is there any term, log term, where I have to move the coefficient that's not 1 to the power position. And it looks like example 2 is the only one. Something else that it says in here, it says if there is more than one logarithm on either side of the equation, you have to collapse or condense that side of the equation into one log, meaning we're going to have to use properties there. So which of these problems deal with that situation? Well, look at problem 3. I have one log term here, but over here I have 2 log terms. Before I can proceed with this strategy, I'm going to have to combine these log terms into one log term. Likewise, look at number 4. One log term here, but 2 over here. I'm going to have to use the quotient to difference, or difference back to quotient property, to rewrite this as a single log. Over here, I'm going to have to condense these 2 by using the product, the product property, where I would go from a sum back to a product. Look at example 5. Okay, this log term, this is a log term by itself on the right-hand side of the equation. I'm going to have to condense these 2 log terms. In order for us to proceed with this strategy, we need one and only one log term on each side of the equation, and likewise down here. All right, so looking at example 1, 2 things are satisfied. The coefficients on all the log terms in this equation are 1. Good. We only have one log term on each side of the equation. Good. Okay, so what do we do from there? Well, we can remove the bases. If this is log base 3 and this is log base 3, I can remove one log from each side of the equation. When these are removed, I set the arguments equal to each other. 3x minus 2 this argument equals this argument. Solving this algebraic equation, before I box this and say it's a solution, I need to check this proposed solution. What that means is take this 2 and put it back into the original problem wherever you see x, and think about what this number is. Is it positive? Because this is an argument, and it has to be positive. 3 times 2 is 6. 6 minus 2 would be 4 if I were to check 2 in the original problem's x position. 4 is a positive number. This is a good solution, and I'll box it. Let's just say that when you plug 2 back in, you got a negative number. How would we indicate that that's not a solution? Well, we'd just lightly cross this off. I wouldn't erase any of my work. You're actually showing the correct mathematical process and getting an answer, but you're showing by crossing it off that you're discarding that solution, or you're discarding that proposed solution. Okay, example 2. I want to solve this log equation. I see a log on both sides of the equation, and just one log term on both sides, but the problem is I've got to move that 3 out of the way because I can't have a coefficient other than 1. We have a log property that says move that 3 to an exponent. When you get to this point in the presentation of the problem is that you have a 1 log on each side of the equation, you can remove the logs and you have x cubed equals 125. A couple ways to solve this. You might already know that the answer is 5. Just because you know you have to take 5 and cube it and get 125. If you can mentally figure out that answer, perfect. But don't forget to go back and check this proposed solution in the original problem. When you plug in 5 for this x, 5 is positive, so that's a good solution. That's the answer. Mathematically, how could we solve this if you didn't know what this answer was mentally? A couple of ways. You could bring in the cube root on both sides of the equation. If this is a third power, bring in a cube root. If you know how to find the cube root on your calculator, wonderful. Go ahead and apply that. And what you're going to see is you're going to get x equals 5, which is what we got by using our mental math. Okay, another way to solve this, instead of bringing in a cube root, is to do something we saw way back at the beginning of the year. Okay, if I want to get this exponent to be a 1 on this x, I could bring in the reciprocal power on both sides. So I could take x cubed and I could take 125 and I could raise both sides of this equation to the 1/3 power. 3 times 1/3 is 1, so I end up just getting x. Now on your calculator, if you're going to find this value, be careful, take 125 and then find the raised 2 key, but make sure that you're putting a fractional exponent in parentheses. And if you do that, you will also get x equals 5. Okay, number 3. No coefficients other than 1 in front of these 3 log terms, but we have 2 over here. Let's collapse these. So I'm just going to bring down the left-hand side of the equation right now and do some log property work here. When I'm adding 2 log terms, actually what happens is I go back to a product of these 2 arguments. So I can condense this into log, and then I'm going to multiply 2 times 2x plus 3. So I'm going to go ahead, that's an easy multiplication. I'm going to distribute the 2 into the 2x, getting 4x, distribute 2 into 3, and get 6. I'm trying to front load this, trying to get some work done on the front end. Okay, notice that we have a log equation, just 1 on both sides of the equation. Now you can remove the logs. And then we just want to finish solving this equation for x, and then as a final step, check our proposed solution. I'm going to subtract a 4x from both sides. This will collect to x, bring down the plus 1, bring down the 6, subtract a 1. Okay, before I box that, because it's either going to be a box or cross off, plug in 5 here to the original problem for x. This is going to be a positive number. We're good here. Plug in 5 here, multiply by 2, add 3. 13 is a positive number. Good, check. And that's already positive in the problem, so we're good to go. If either one of these returned a negative number when I checked 5 in for the x, then the whole problem, this solution wouldn't work for the entire problem. Okay, number 4. We'll do this last one, and then I'll have to start another video to finish the rest of this. All coefficients are 1. I have 1 log expression over here, but I have 2, so I'm going to have to use a property to condense. I see a subtraction, not an addition, so that means this problem right here is going to go back to a quotient from section 4.3. So build a fraction. What goes on top? 7x minus 23. And then what follows the subtraction sign, the argument, goes down here. I have 1 log on both sides of the equation. Let's remove them. I'm going to set x minus 3 equal to this fraction. So let's go ahead and make x minus 3 a fraction. The strategy to solve this mathematically, for me, you can multiply both sides of this equation by x plus 1. Another strategy is I'm just going to cross multiply. So just be careful when you cross multiply here. Ooh, it's going to be a little bit longer. 1. So I'm going to multiply x minus 3 times x plus 1 equals, this cross product is just 7x minus 23. Real quickly, I'm going to FOIL these. I think the result is x squared minus 2x minus 3. Okay, now to solve this equation, notice we have a quadratic term. So our strategy mathematically isn't what we did here. I'm going to zero out one side and try and factor. So that means I'm going to subtract a 7x. So I'll put it underneath this term. And then I'm going to add a 23 and put it underneath this term. So these will cancel. These will cancel. I need the 0 over here. Bring down the x squared. Bring down the minus 9x. The plus 20. For this quadratic equation, you can use quadratic formula. You can try and factor it. I think I'm going to try and factor it. I think there are factors of positive 20 that sum to negative 9. So remember, a times c and then b. So factors of 20 that sum to negative 9. You could list all the factors in order if you want, but you're eventually going to stumble on 4 and 5, where both of them need to be negative. So I'm going to have x minus 4 and x minus 5. Set each factor equal to 0. So here the result is going to be x equals 4 and x equals 5. Before I box either one of these or both, I need to check one at a time 4 in for the x here, here, and here. Meaning when I plug 4 in here and I subtract 3, that number 1 is positive. So far, so good. When you plug in 4, you're going to get 5 as a result. 5 is positive. So far, good. When you plug in 4 here, you're going to get a positive number. So 4 is a good answer. Also, when you check 5, the result in all the arguments is that you do get a positive answer. Okay. We'll pick it up in the next video to finish these.